friends, I welcome you all on India's largest live e-learning educational platform, that is Gradeup. A to Z, thank you so much for waiting for me. First of all, please tell me whether my audio and visual quality is okay for you so that we can proceed for the session. A to Z, please tell me whether my audio and visual quality is okay for you so that we can proceed for the session. Venkat, how are you? Please tell me whether my audio and visual quality is okay for you so that we can proceed for the session. Okay, so Subramaniam is reporting that my audio and visual quality is okay. Now let us proceed for the session. Friends, before I start today's session, let me tell you that today is the last date. Today, 25th of April, is the last date to enroll for GEST, that is the Gradeup Engineering Scholarship Test, that is going to be conducted on 11th of May. And if you are among the top 50 students, then you will be eligible for very attractive scholarships. So all the candidates, if you have not registered till now, it is better that you register today itself. Today is the last date. All of you, thank you so much for joining me in this session. Let us start this session. Before I start this session, let me tell you that today we are going to start. Let me list out the topic that we are going to cover today. We'll be starting with the basic construction of the transformer. Then we will see transformer action, equivalent circuit, and if time permits, then voltage regulation. Otherwise, voltage regulation we will keep for the Monday class. We are not in a hurry. We will be covering each topic with utmost detail so that your learning can be enhanced. That is the idea. So now let us start with the session. The first slide on your screen shows how to wash your hands so as to protect yourself and others against the infections related to the novel coronavirus. This is the initiative started by Team Gradeup as #PrepSmart Stay Safe, under which we are communicating to our students how you should wash your hands in the best possible way. These are the steps. You should wash your hands under the direct tap water, apply soap, rub hands palm to palm, lather the backs of your hands, scrub between your fingers, rub the backs of the fingers on the opposing palms, clean thumbs, wash fingernail, fingertips, then wash your hands under the direct tap water, dry it using a towel and switch off the tap by using a tissue paper or the towel, and now your hands are clean, and this whole procedure should approximately take 20 seconds as per the government regulations. Good evening all of you. Good evening. The second slide on your screen shows the contact number for the control room which is being set up at the national level to address the queries related to the novel coronavirus. You may reach this number for any guidance, support and technical queries. This also we are communicating under the initiative #PrepSmart Stay Safe as started by Team Gradeup. There is one more important information for all of you, that Gradeup is going to conduct the BYJU'S Steel 2020 Mega Mop Challenge. That has already been opened today itself, 25th of April. It is going to be open, remain open till 26th of April, 12 p.m. That is a 24 hours window. So if you are interested, you can attempt it now. That is very, very important, and you can know what is your rank. Next important information is about the free of the cost classes Gradeup is offering in the classroom, Gradeup classroom. For example, electrical engineering, M. Ramesh Sir, Chandan Sir and Rakesh Talreja Sir, they are taking the engineering services 2020 mains practice classes at 9 am in the morning. Chandan Jha Sir is taking concept on fingertips classes at 12 p.m. I am taking engineering ethics classes for engineering services paper 1 at 1 p.m. Monday to Friday. Vijay Bansal Sir is taking concept on fingertips classes at 2 p.m. and Amin Ramesh sir is again taking concept on fingertips classes at 7 p.m. It's okay, Adi. Now, one more important information about this Target Gate 2021 and Electrical Engineering course. The most important feature of this course is that it is going to be bilingual. It means हिंदी और इंग्लिश दोनों में बातचीत होगी, so that your learning is ensured irrespective of your language barriers. Rakesh Taveja sir, MEIC Bangalore, AIR 9, 10 plus years of experience. Myself Ashutosh Saxena, M.Tech IIT B.H.U, 10 plus years of experience. Amin Ramesh sir, ME Usmania University Hyderabad, 17 plus years of experience. Vijay Bansal sir, 19 plus years of experience, and Chandan Jha sir, M.Tech NIT Hamirpur, 9 plus years of experience. So many students have started the free trial. If you are interested, you can also start the free trial. Good evening, all of you. So we are going to start transformer, but yesterday's question I will be continuing from there only. Yesterday I asked a very basic question. Why we are so much worried about this transformer? So many candidates gave different answers. But the real idea is, if you see, transformer is such a beautiful device. It is available from 1/10 of a gram to hundreds of tons in weight. If any device is available in such a wide range of sizes, that is from tens of a gram to hundreds of tons, then you can imagine its potential, then you can imagine the utility of this beautiful device. What is the beauty of this device? It can step up or step down the input voltage at a very high efficiency. At a very high efficiency. In general, if you say the efficiency of the transformer, it is approximately more than 90%. It is more than 90%. Why? Because there is no rotating part in the machine. Transformer is a static device. That is the first point. Second point, both primary and secondary windings are nothing but inductive coils. Therefore, resistance of the windings is very small, and you can say I square R losses are also very small. Third thing, core material is assumed to have very high permeability. Okay, so exciting current required is very less, and therefore core losses are also very less. Subramaniam is asking, sir, what are the best book for practice electrical machines problems? See, I can tell you the first thing you have to do is you have to go with the basic part of theory, and if you are okay with that, then you can go and solve the solved example of P.S. Bimra, Nagraj Kotari, that is the basic books. Beyond these books, you are not required to go. If you are comfortable with these basic books, P.S. Bimra, Nagraj Kotari, all these, then I think it is sufficient for you. Vikas Pal is asking, sir, define permeability. Beta, this mu is defined as the permeability of the magnetic material, and the explanation of this mu you can define like this. It is the ability of the magnetic material to give way to magnetic flux. I hope it is clear. What is the meaning of this? The meaning of this is, as mu r, that is the relative permeability, is going to be very, very high in comparison to 1, the magnetizing current to set up flux in the core is almost negligible. That we will understand in due course of time. Just have a little bit of patience, we'll understand all these things. Permeability is the ability of the magnetic material to give way to the magnetic flux. The more is the permeability of the magnetic material or the medium, the less exciting current is required to have flux in the core. For example, if you take this example, suppose at particular time no load is connected here. If no load is connected here, so suppose I2 is going to be 0 at any point of time. So if no load is connected here, it is the no load condition, it is the open circuit condition at the load side. So at the primary side or the supply side, only no load current is going to be present. Yes or no? Now some part of this no load current we are calling as magnetizing current. What is the magnetizing current? Magnetizing current is the current required to set up the flux in the core, that is the flux phi. Now if your mu r value is very, very high, we are assuming infinite for ideal transformer. If it is very, very high, it means the magnetizing current component of the no load current, it is very less. With just a very, very small, almost zero magnetizing current, you can set up the flux in the core. That is how we are defining the permeability. Ray Lone is asking, sir, what is eddy current? Beta, see, if you ask me like this, what is permeability, what is eddy current, if you ask me like this, then it is going to be a very difficult session for me to take up. First, you listen to me with all your patience, and then if you have any doubt, then you are most welcome to ask your doubts. I hope it is clear to all of you. We'll discuss all these things, beta, Ray Lone. When we will discuss the efficiency of the transformer, we will discuss what is eddy current and all that. Okay? Just have a little bit of patience. Now you just see on your screen, this is the general transformer configuration. You can see on your screen some important parts are mentioned here: conservator, breather, explosion vent, cooling tubes, Buchholz relay, all these things you can see. These are the bushings, you can say, all these things you can see. So some small things we are going to discuss about the transformer, but before that I want to give you some practical understanding of the transformer. Okay, the transformer works on the principle of mutual induction. The transformer works on the principle of mutual induction. Sanjay, you know what is the formula for reluctance that we have already covered in our previous class, and you should be knowing if permeability is high, then what should be the reluctance? What is reluctance? Obstruction in the path of flux. If you are saying permeability is high, it means the obstruction in the path of flux is less. So reluctance is almost zero. If you are assuming that your permeability of the medium is infinite, then you can say that your reluctance is going to be zero. And you should also be knowing the formula of the reluctance. So from there also you can derive it. So first point is, the transformer works on the principle of mutual induction. Second, the two windings, in general there are two windings in a transformer. If you are talking about the two winding transformer, except the auto transformer we will discuss separately, but there are some special cases where we use tertiary winding also, that we will discuss in due course of time. Just please try to understand the two windings of the transformer are not connected electrically. Third point, the two windings are coupled through the magnetic coupling due to the presence of flux in the core. All these are small details that we are going to discuss. Okay, now some important parts we are going to discuss, the parts of the transformer. Now first we are going to discuss the cores. Now very quickly we will be covering these small parts, so just have patience and listen to me. What is core? See, core is going to be looking something like this. You can see that core we are using laminated core. What is the meaning of laminated core? Instead of having a solid structure, we are having strips, and those strips are laminated and they are coupled together to form the core. So you can see the transformer core is made up of iron, silicon, steel or other ferromagnetic material. The iron ore is made up by thin metal strips, this is important, and lamination insulated by a coat of varnishes or the paper. Each metal strip has a thickness near about 0.5 mm. Okay. Now if you see, there are different type of laminations that can be used. Basically L and E type laminations are used in different types of the transformer. If you see the core type of transformer, we'll discuss what is core type transformer, what is shell type transformer. Don't worry here, we'll discuss all those things in details. You just listen to me properly. If you see the core type of transformer, then we are going to use the L or U shaped laminations like this. This is for core type. And if you see this E or I shaped lamination, this is basically we are using for the shell type transformer. I hope it is clear to all of you. Now let us see the cross section of the transformer cores. Now the transformer cores can be rectangular, squared, or they can be stepped core. Stepped core is also we are calling as, stepped core. I am writing here. It is sometimes also called cruciform. Okay. So what is the purpose of having the stepped core? The stepped core advantage, I am just giving you one line. Rest details we are going to see later. It gives saving in the conductor material and losses are reduced because you are using less copper, so obviously losses are also going to be reduced. What is the overall idea? The overall idea is, suppose if you are using a square core, then you require a larger cross sectional area. Now if you want to reduce this cross sectional area, then we are going to use the stepped core in this form. This is also we are calling as cruciform core. I hope it is clear to all of you. Now let us quickly see this. What is this tap changer? Tap changer means on the high voltage side, generally on the high voltage side, some taps are there so that you can choose the required voltage from the winding. The tap changer used to regulate the supply voltage or the load or maintain both the conditions by changing the turns. See, your transformer is nothing but changing number of turns gives variable voltage. The tap changer can occur on the primary side or the secondary side, but generally if you see, the tap changer is used on the high voltage side, and that is very obvious reason. Now you must be knowing this, that tap changer are available in two categories: no load tap changer and on load tap changer. What is transformer tank? The transformer tank, you can say it is a cylindrical shaped tank. It is made of steel metal with a high thickness. The core and the transformer winding is placed in the transformer tank. The transformer tank stores the oil, especially the mineral oil. This oil provides the insulation and cooling to the transformer winding. See, on YouTube beta, don't provide PDF RD beta, it is already available. I am just taking a very small part so that you have a basic understanding of different parts. Okay, it is just a requirement, a prerequisite, so that we can start the transformer. What is conservator? The oil conservator tank looks like a rectangular tank. It stores the extra oil and directly connected with the transformer tank. The oil conservator tank plays an important role in the transformer. The purpose of conservator tank is to protect the expansion of the oil in the main tank of the transformer. This is very, very important. The oil used in the transformer, it serves two purposes. Number one, insulation. Number two, cooling. When the oil level reduces due to losses or the leakage, the conservator will be delivering oil to the transformer. So it acts as a reservoir of oil. Now let us see what is the breather. Breather is connected with the conservator tank. This is very, very important. It can be asked in some small examination. Where breather is connected? Breather is connected to the conservator tank. Why it is connected to the conservator tank? Now you see what is the purpose of breather. It is the cylindrical vessel which is filled with blue color silica gel. They have two purposes. Number one, remove the moisture from the air and to have the capacity to absorb the moisture in the transformer. So to contain the moisture in the transformer, it is connected to the conservator tank. It plays a role to act as the air filter and to provide the free moisturizing air to the conservator tank. You all must be knowing about this. Yes, Ranjit Mahal, it can be of different shapes. It can be of different shapes as per the requirement. In general, you please have the general understanding. Okay, Ranjit Mahal beta, we'll see what types of oils are going to be used. There are so many range of oils which are used. For example, mineral oil are there and so many other categories are there. That we will see. Just wait for the time. You can't you have a little bit of patience? Now the Buchholz relay, the most famous relay which is used for the protection of the transformer, it is actually a gas operated relay, and you must be knowing that it senses the fault before it occurs. It can sense the incipient fault also. Suppose the fault is slowly occurring inside the transformer winding, the Buchholz relay has the capability to detect the fault before it actually appears. Now, what are the bushings? The bushings is an insulating device. In general, you can say it is an insulating device. You all must have seen in your locality the transformer. It is something brown shaped. You can say dark brown shaped. Insulation is there, which is used to keep the terminals out of the transformer. It is made up of porcelain material. The terminal of the bushing is provided a path of the conductor to the transformer tank. With the help of the terminal, the transformer gives and provides supply to the another system. These are the important points I wanted to cover here. Now we are going to start with the transformer. Now first you have to understand what is the dot convention. I hope it is clear to all of you. See, the transformer action requires that the two coils of the transformer should have a subtractive polarity, that we will see in due course of time. Subtractive polarity. So what is the dot convention? If the current enters the dot on one coil, then it leaves the dot on the other coil. What is the idea? See, transformer action we'll just read. Don't worry about this transformer action. What is this transformer action that we are going to cover in today's lecture itself? So please have patience. Now please try to understand what is the dot convention. Let me give you an example so that you understand it better. Okay. Now suppose it is a transformer core. Suppose it is a transformer core. Okay. And suppose these are the windings. Okay. Suppose This is the supply side. You are providing the AC supply here. You are providing the AC supply here on this winding. This is winding number 1, this is winding number 2, this is winding number 3, this is winding number 4, and all these 2, 3 and 4 loads are connected. Suppose load 1 is connected here, load 2 is connected here, and load 3 is connected here. Okay. Now suppose the question asks you, place the dots for the load side winding as per the transformer dot convention. What is that dot convention? The dot convention for the transformer is, if the current enters the dot at one winding, that is the supply side, then it is going to leave the dot at the other winding or the load side. Now if you see that if current is going to flow in this direction, that is current is entering the dot, here we are saying that current enters the dot for this supply side, then for this load 1, load 2 and load 3, the current should leave the dot. Yes or no? Now first we will understand how the flux is going to set up in this winding. Now please try to understand. If you see, because of this current, suppose this is I1, suppose this current I1 at the supply side, it is going to flow in this direction. The current sense for the supply side or this winding, it is going to be like this. So if you want to know the direction of flux set up by this winding, how you are going to do? You are going to apply the right hand rule. What is the right hand rule? You are going to move the right hand finger in the direction of the current, and your thumb is going to point towards the direction of flux. I hope it is clear. I am writing it here. What is the right hand rule? The right hand rule is, place the curved fingers in the direction of current sense in the winding. What is the second point? The thumb points the flux direction. Yes or no? Are you getting this? Now let us go back and try to understand. If you apply the right hand rule, the movement of or curving of your fingers of the right hand in the direction of current for this winding where I1 current is there, then the direction of the flux setup is going to be this direction. Yes or no? It is going to be in this direction. So it is going to be clockwise. I hope it is clear to all of you. This is going to be the direction of flux. Yes or no? Now if you see these 2, 3 and 4 windings, the current sense in these windings should be in such a direction so as to oppose this flux set up by the primary winding or the supply side winding. Yes or no? So what is going to be the current direction in this? Please tell me what is going to be the current direction. You just apply your right hand rule. If it should oppose this flux, then it should be in this direction. So you are going to curve your fingers like this. So the current direction is going to be in this direction. Now because it is a load side, so current should leave the dot. So dot is going to be placed here. Similarly, for this winding, if it has to oppose this flux, then what should be the direction of current? Apply the right hand rule. So the current sense is going to be in what direction? The current sense is going to be in this direction. Yes or no? The current should leave the dot, so the dot is going to be placed here. Similarly here, the current sense should be in this direction. And current should leave the dot, so we are going to place dot like this. Now all of you, please tell me whether this understanding of the dot convention for the transformer, are you comfortable with this? And if you have any doubt, then you can ask me. Are you comfortable with this? Please tell me quickly. With this dot convention, are you comfortable? All of you, please tell me quickly. I can try to answer your doubt if you have any doubt. Otherwise, we are going to proceed. What about other candidates? Okay. So now let us proceed. It's okay, it's okay. Now we are going to discuss something which is very, very important to understand the transformer, that is self-inductance, mutual inductance and leakage inductance of the coil. It's okay? Okay, some people are having doubt. Now please try to see. I am saying, I am writing it here, please try to understand. I am repeating it. That the supply side you are providing current I1, yes or no? And the current is entering the dot, suppose. It is given in the problem. And you have to find the placement of the dot for the load windings. Winding number 2, 3 and 4. How you are going to do it? First you have to find the direction of current. Yes or no? First you have to find the direction of current. Definitely the current can only flow if the circuit is complete, if the load is connected. Yes or no? So if you see that current which is going to flow in the load side windings, it is going to generate a flux which is going to oppose the main flux in the core of the transformer. What is that main flux? That main flux is the flux set up by the supply side current. So if you see, for this load 1, it should oppose the flux in this direction. Yes or no? It should oppose the flux in this direction, and if it has to have a flux opposing to this main flux, then what should be the direction of current? Apply your right hand. Movement of the fingers across the direction of current and the thumb in the direction of flux. So it is going to be this direction. Similarly, you can do it for winding 3 and winding 4. See Ranjit Mahal beta, it is vice versa. It is vice versa. It is vice versa. What is the meaning of vice versa? Vice versa means, suppose if the current is leaving the dot at the supply side, so on the load side the current should enter the dot. The basic idea is that because of the transformer action, we will discuss this. We will discuss this transformer action today itself. What is this transformer action? Don't worry, just have patience and stay with me. This transformer action we are going to discuss. Because of this transformer action, the two coils of the transformer should have a subtractive polarity. For that purpose, we are having this dot convention for the transformer. I hope it should be clear to all of you. Sanjay Bontu is asking, sir, if aiding, then what is going to happen? Beta, let me tell you, for transformer action, it is not possible that it is going to aid. Until and unless you connect some source here. Until and unless you connect some source here. I will tell you this thing, please have little patience. Let me discuss and when we will come to this transformer action, then we will discuss. Now we are going to discuss this very important thing, that is self, mutual and leakage inductance. Let's try to understand it again. Let me draw the diagram. Suppose this is your transformer core. Okay. Suppose this is your primary winding. And suppose this is your secondary winding. Okay. Suppose you are connecting is AC source here. You are connecting an AC source here. And here this is switch. And suppose this is load, some load, this is switch S. And suppose because of this there is some current I1 is here. So suppose there is some flux in the core like this. I hope you are getting this. Suppose this is phi m. What is phi m? Mutual flux. I hope it is clear. What is mutual flux? What is the mutual flux of the transformer? Which is linked with both the primary and secondary windings. Yes or no? But there is going to be some leakage flux also. Suppose we are talking about the practical transformer. For a practical transformer, there is going to be leakage flux. What is leakage flux? Flux which is linked only one of the two windings. I hope it is clear. Suppose if you see, this we are calling as phi L1. What is phi L1? Leakage flux for the primary winding. This we are calling as phi L2. What is phi L2? The leakage flux at the secondary winding. I hope you are getting this. It is going to be phi L1 for primary winding, and it is going to be phi L2 for the secondary winding. Are you comfortable with this? I hope you are comfortable with this. Now I am going to write the primary leakage inductance. How I am going to write the primary leakage inductance? Suppose I am writing it like this: LL1 it is going to be N1 d phi L1 upon di1. Can I write it like this? Can I write like this or not? This is the leakage flux. Yes or no? Please listen to me properly. What is the leakage flux? It is phi L1. Now this phi L1 is linked with one turn. How many number of turns are there? Suppose here it is, how many number of turns? Suppose here it is N1 turns and here it is N2 turns. So if phi L1 is the flux linked with the one turn at the primary side, so the total flux linked is going to be how much? Total flux is going to be multiplied by N1. This is the total flux, leakage flux linked with the primary winding, and this is the current, you can say, in the primary winding. In terms of differential we are writing. I hope it is clear to all of you. Can we write like this? So this is very, very important. Please try to understand how I am writing this. In general, if you want to write the inductance, what is this? It is the total flux divided by the current. What is the total flux? Differential leakage flux multiplied by N1 divided by differential current I1. I hope it is clear to all of you. Now I am going to write the differential reluctance. Offered to phi L1. It is going to be how much? The reluctance for the leakage flux we are writing as N1 di1 upon d phi L1. Now please try to understand how we are writing it. We are writing reluctance as MMF divided by flux equation. I hope you remember this equation. Very basic equation. Reluctance is going to be MMF divided by flux. So we are writing this like reluctance offered to the leakage flux is going to be differential 1. Now some of you may be having this doubt. Why we are using this differential term? Why we are using this differential term? Now please try to understand. When you talk about the leakage flux, it is very difficult to model. When something is non-uniform, when something is very difficult to model, we generally go for differential approach. That is why we are using the differential approach. I hope it is clear to all of you. So if you follow these two equations, suppose this is your equation number 1 and this is your equation number 2. From equation 1 and 2, you can write the leakage inductance as N1 square upon RL1. This is the general formula. You remember this or not? This is the general formula for leakage inductance for the primary winding. This is very, very important. Suppose we call it equation number 3. And similarly, you can write for the leakage inductance for the secondary winding. Directly you can write yes or no. You can write it or not. What is going to be LL2? Can you tell me? It is going to be N2 square divided by RL2. What is RL2? Reluctance offered. What is RL2? Please tell me. It is the reluctance offered to the path of leakage flux in the secondary winding. So this is going to be your equation number 4. Very important. Now if you want to write, let us see mutual inductance. Let us see mutual inductance. How we are going to write it? Please see. I hope you all are okay with this. You can follow this. If you have any doubt, then you can ask me. For mutual inductance, I am writing. See, the EMF induced in the secondary winding. How EMF is going to be induced in the secondary winding? Please tell me why. This we will understand. What is the transformer action? After that you will understand. But for the time being, you please understand that the moment you apply some voltage V1 here, there is going to be some EMF induced in the primary winding that we are calling as E1, and because this current is flowing here I1, there is flux is, this current is sinusoidal AC, so this flux is also going to be sinusoidal, yes or no, alternating. And because this flux is going to be alternating, my dear friend, there is going to be some EMF induced in the secondary winding. As the switch is open, no current is going to flow at the secondary side, but at least right now some EMF is going to be induced. That is the idea. Is it clear to all of you? So how you are going to write the EMF induced in the secondary winding? Use the Faraday's law. So this is going to be N2 d phi m upon dt. Are you getting this or not? What is phi m? Phi m is the mutual flux, and that mutual flux, because of the current in the primary winding at the supply side, there is going to be some flux in the transformer core, which we are calling as mutual flux. Why we are calling it mutual flux? Because this flux is going to be linked with the secondary winding, and because this flux is time varying, it is going to induce some voltage in the secondary winding that we are writing by using the Faraday's law and d phi m by dt. I hope it is clear to all of you. Now this you can write as N2 d phi m upon dim multiplied by dim upon dt. What is this Im? Im we are writing as the magnetizing current. What is magnetizing current? To establish flux in the core. Ranjit Mahal is asking, sir, sign is not applicable. Listen very carefully. Listen very carefully. Ranjit is asking a very genuine doubt. He is asking, in general we use the negative sign here. Why we are not using the negative sign here? Beta, we are not using the negative sign here because we have already taken care by using the Lenz law in terms of dot convention. We have already taken care of this negative sign by using the Lenz law, using the dot convention. That is why we are not using it. And you just wait for the moment when we will discuss the transformer action, then you will understand why we are not using the minus sign. The books which are using the minus sign here, they must mention it, because you cannot do the same thing two times. One time you are saying the dot convention, and at the other side you are saying the minus n d phi by dt. That is wrong. You have already taken into account the minus sign by using the Lenz law. This minus sign only represents the Lenz law. What is the Lenz law? The effect opposes the cause. I hope it is clear to all of you. So if you can write this induced EMF like this, if you can write this, then I am writing it like this. Please try to write it here. So it is going to be, what is this? N2 d phi m upon dim. This we are writing as M21. I hope it is clear. What is the mutual inductance of the second coil with respect to the first coil? It is the mutual inductance of the first coil with respect to the second coil with respect to the first coil. How you write the mutual inductance? You tell me. It is the flux linked in the secondary coil. That flux is going to be M phi21 divided by the current in the primary side. So primary side, that is the magnetizing current Im. And what is this phi21? This is nothing but phi m. So by using this formula for the mutual inductance, we are writing it like this. So your E2 is beta going to be how much? It is going to be M21, and this is going to be dim upon dt. I hope it is clear to all of you. What is the equation number? So this is going to be equation number 5. I am just removing my photograph so that you can see the content on the screen. I will put it again. Okay. Now you see here this M21 we are writing as, that is the mutual inductance of second coil with respect to the first coil, as N2 d phi m upon dim. Yes or no? And this you can write as N2 N1 upon Rm. What is Rm? Rm is the reluctance to the path of mutual flux. What is Rm? Reluctance to the path of mutual flux. Is it clear or not? Flux divided by the current. Do you remember this or not? Flux is going to be mmf divided by reluctance. So this current divided by this flux we are writing as reluctance. I hope you are getting this. Please wait for the time, Ranjit Mahal. Don't do the short circuit. We are just trying to understand the transformer, and if you short circuit our transformer, what is going to happen? Just wait for the time. We will consider all these conditions we are going to discuss. First you understand this. Are you comfortable with this? I hope you are comfortable with this. Now I am just writing on the new page so that you can understand it better. We'll see transformer action after some pages. Is it okay? Now we are defining reluctance R1. Okay, what is reluctance R1? We are defining reluctance R1 how? It is the total reluctance of the parallel path of two fluxes. Okay, that is phi L1 and phi M. Now let us come back and see what is this. If you see this transformer, you can see this mutual flux phi M and this leakage flux phi L1. Can you see this acting as a parallel, yes or no? So we are writing the total reluctance like this. You can consider it as the two resistances connected in parallel. I hope it is clear to all of you. And this we are relating by a coefficient K1 as R1 upon Rm. I hope it is something new that we are discussing. Very less people discuss it, so there it may be little difficult for you to understand at the first place, but if you understand it, then it is going to be easy for you. How we are defining the total reluctance? Total reluctance of the parallel path of the two fluxes at phi L1 and phi M. Are you getting this? One path, one parallel path. When the current divides, we call it parallel path in terms of electrical circuit. When the flux divides, we call it parallel path in terms of magnetic flux or the magnetic circuit. Yes, from here we are going to define the coefficient of coupling, don't worry. So if you see, now if we want to write the self-inductance of the coil, suppose now we are trying to write the self-inductance Gonda Kavya is saying, sir, once again please. Okay, now listen to me. We are defining R1 as the total reluctance of the parallel path of the two fluxes. Now let me show you the two parallel paths. Let me show you the two parallel paths. You just focus here. You just focus here. For this leakage flux, it is like this, yes or no? So there is going to be some reluctance associated with this that we are calling as RL1, yes or no? And there is another flux, mutual flux, so that we are writing as RM. So these are the two reluctances and they are connected something like this. You can understand like this. Are you getting this or not? And what is the total MMF here? Total MMF here is going to be how much? N1 I1. And when the secondary is open circuited, this is going to be nothing but N1 IM. I hope it is clear to you. What is IM? IM is going to be the magnetizing current. N1 IM. This total MMF at the primary side is going to act like a voltage source. And there are two fluxes. One flux here, it is going to be leakage flux. One flux here, it is going to be the mutual flux. And it is going to act like a parallel path. This is how we are trying to model the leakage flux. I hope now you can understand it. Now I am going to write the self-inductance of the primary winding. Self-inductance of the primary winding. And it is given I2 is equal to 0. It means secondary is at no load condition. So you must be knowing this formula that L1 you can write as N1 square. It is going to be N1 square upon reluctance R1. That is the total reluctance, yes or no? This you can write as N1 square. We are writing it like this, N1 square upon R1, just multiply and divide by Rm, and N2 like this, multiplying and divide by this Rm N2 upon Rm N2. And if you simplify this, then you will get the self-inductance as Am upon K1, where this M is the mutual inductance between these two coils. Similarly, you can write the expression for M12 and M21 also. I hope it is clear. So this is going to be your final expression for the self-inductance. Suppose it is equation number 6. And similarly, for the secondary side, for secondary winding, you can write another coefficient K2 as R2 upon Rm. What is the R2? It is the total reluctance of the parallel flux paths, leakage flux at the secondary winding and the mutual flux. I hope it is clear. So you will obtain the self inductance of the secondary winding as M upon A K2, that is equation number 7. Here this A we are defining as the turns ratio. I hope it is clear to all of you. Now if you see equation number 6 and 7, from equations 6 and 7, if you see, then you can write the equation for M as it is going to be under root K1 K2 and this is going to be under root L1 L2. This we are calling as K, which K is nothing but coefficient of coupling or mutual coupling. I hope it is clear to all of you. In general, you can say the values for a practical transformer, it is going to be something like this. So the coefficient of coupling is also going to be lying between 0 and 1, and for K is equal to 1, it means the perfect coupling. The leakage flux is going to be 0. If the leakage flux is going to be 0, it means it is going to be the ideal transformer. It is going to be the ideal transformer. And this is for the practical transformer. All of you, please tell me, are you comfortable with this? And if you have any doubt, then you can ask me. Whatever we have discussed till now, if you have any doubt, then you can ask me. All of you, can't you increase the number of likes and shares, my dear friend? Yes, RD, perfectly right. You are perfectly right. All of you, can't you increase the number of likes? Please increase the number of likes, and if you have any doubt, then you can ask me. Otherwise, I am going to discuss the transformer action. Please tell me yes or no. Are you comfortable with this? I know that it is little bit apart from what you study in regular for the transformer, but it is something which can be asked in your engineering services examination. That is very, very important. How you are going to define the inductance? Self-inductance, mutual inductance, leakage inductance. We are going to model the leakage flux in terms of leakage inductance. That is very, very important, how you reach to the equivalent circuit of the transformer. All of you, please quickly tell me whether my audio and visual quality is okay. Can you listen to me? Beta, what do you want me to repeat? Ranjit Mahal, you cannot say, sir, repeat the whole lecture. You cannot say like this. If there is any confusion at a particular point, then you can ask me, sir, please repeat this point. If you go to a doctor, then you, may God forbid that you go to a doctor, just I am saying any XYZ, then you have to tell the doctor what is the exact problem, then only he can solve it. You cannot say just, sir, repeat it. All of you, please tell me if you have any doubt. Otherwise, we are going to discuss the transformer action. And I can see, can't you increase the number of lights? Very less. Anyways, Ranjit Mahal is saying mutual induction. Now I can answer you. What is mutual induction? Mutual induction says, suppose there is a current I1 in this winding. Number of turns are like this, N1, N2. Okay. Suppose because of the current I1 in this winding, there is going to be some flux. And if this flux is linked with this coil, there is going to be some EMF induced here. Yes or no? How this EMF is going to be induced in this secondary winding? Because this flux is linking this winding. This flux is because of which current? The current in the primary winding. So if you are saying that this is the total flux in the secondary winding due to the current in the primary winding, what is phi 21? Phi 21 is the flux linked in the secondary winding due to the current in the primary winding, and if you divide it by this current, then it is going to give you the mutual inductance of the secondary winding with respect to the primary winding. This is how we are going to define the mutual induction. Now let me tell you very important point. The transformer action that we are going to discuss, it is only possible because of the mutual flux or the mutual induction. Your transformer is all about mutual induction. I hope it is clear to all of you. Now I think we are running short of time, so I will be taking up this transformer action and the rest of the topics in the Monday's class, next class, because I can see that the time is already, we are running more than the scheduled time. So let us conclude now. You better focus till here. You read this, whatever we have discussed till now, and if you have any doubt, then in the next class we are going to discuss it. And from Monday onwards we will be discussing some different topics related to the transformer. Now there is some important information regarding this target batch. I have already explained it is a bilingual course, and I have already told you the last date is today, that is 25th of April. You should enroll yourself today itself if you want the scholarship. What is the procedure? The procedure is you have to go to the Gradeup app. How to enroll? Go to the Buy Now section. Select the monthly installments option. Proceed to pay just 1,000 rupees. Simply just 1,000 rupees, and you will get the access till 15th of May. This is how you can enroll yourself. For any further doubt, you can contact this number or the email ID. It's okay, RD? These are the important features of this Gradeup Engineering Scholarship Test that is going to be conducted on 11th of May. This is for the scholarship of the students. It is going to be end today itself, 25th of April. You have to enroll yourself. You have to attend the live classes, appear for the GST, and your attendance in the live classes and your marks in this test, GEST, that is going to decide the merit. And if you are among the top 50 people in the electrical engineering, then you are going to get very attractive scholarship up to 100%. I have taken a separate session for that, so if you are interested, you can go for it. So Monday we will be discussing the remaining part in the transformer, and if the time permits, we'll go for the efficiency also. These are the 60 plus Gradeup students who have scored in the top 100 in the GATE 2020 examination. If you want, then you can also be there, but you have to work really hard, and you should have that commitment to have your photograph in these toppers. So friends, thank you so much for your time. I wish you all the best for your upcoming exams. Don't forget to join me on Monday. We are going to discuss a lot of interesting concepts related to the transformer action, equivalent circuit, phasor diagram, voltage regulation, efficiency, all those things we are going to discuss. But the most important thing is you should stay in your home, you should stay safe, and you should follow the government regulations. Don't forget to tell me in the comment section if you want some improvement from my side in the next class. If you find any problem in this class, then you can tell me what is the shortcoming so that I can improve upon that in my next class. So I hope it was a value addition class for you. You must have got some new ideas about the transformer, and we are going to discuss some more on Monday 8:30 p.m. evening, right on the Gradeup platform. Prep smart, score better, go Gradeup. Thank you so much.